Okay, we're ready to go here. So, we have 3 more sections to do, and then we'll have an exam. This next one is not quite too bad. It's called Orthogonal Trajectories. Okay, and so far, here's what we've done, or here's what we know. We know that for a differential equation, that's nth order, we can expect an n-parameter solution. Okay, so far we've only really seen first order, and we have one constant or one parameter. We've seen a couple of second order equations via the substitutions that we've done, and we've gotten 2 parameters. So we can expect whatever the order is, that'll determine the number of parameters in our solution. Now, what we're going to try to do is, given an n-parameter family of curves, find the nth order differential equation. So we're kind of going to go backwards, much like when you multiplied binomials, then you learned to factor them. Here we're going to try to figure out what the differential equations look like depending on what kinds of functions we're dealing with. So, here's an example to illustrate this point. We'll do one that we're already familiar with. Let's say we want to find the differential equation of the family of curves y equals c1 e to the x. Okay, so the idea here is, if we differentiate both sides, we introduce our differential dy dx on the right hand side, which is get c1 e to the x times dx dx, or 1. And now, from here, take the original equation. What's c1 going to be? Y over e to the x. Okay, so the idea here is that we need to get rid of the parameter so we can see what the differential equation looks like. And knowing what the family of solutions is going to look like already, we can do that. So we get c1, plug it into the differential equation. So we get y over e to the x times e to the x, which of course gives us dy dx equals y, which we hopefully already knew, right? But that kind of illustrates the idea of how you would go about finding the differential equation. So you're going to be given a function. You're going to want to go back and see what kind of differential equation would give you that solution. And you can do that by isolating the parameter, plugging it in, taking the derivative. Okay? Any questions on how to do that? Okay. So, where is this headed? Well, let's talk briefly about orthogonal curves. And the idea here is that 2 curves, let's call them C1 and C2, well, those are going to be orthogonal at a point if and only if their tangent lines let's call them T1 and T2 are perpendicular at the point of intersection. So, I mean, just to illustrate what this means, let's say we have curve 1. Let's say this is curve 2. And the question is, right here at this point of intersection, we want to know if these two curves are actually orthogonal to one another. Okay, we can do that as long as we know their tangent lines. So let's say this would be T2. And then tangent line for the first curve looks something like this. Okay, as long as these two tangent lines are perpendicular, then C1 and C2 will be orthogonal, and vice versa. If we know they're orthogonal, then that means that the tangent lines of those two curves will be perpendicular. Okay? All right, let's try an example illustrating this point before we put everything together. Show that y equals 4/3 x, and let's say the circle x squared plus y squared equals 25 are orthogonal at their intersections. Okay, so let's talk about what to do first, and then we'll go ahead and do it. Bless you. Is everyone caught up to the example? Can I get rid of this page? All right, so how do we show that these things are orthogonal to one another at their point of intersection, or points of intersection? Yes?
We find dy dx.
That's one half of it. Find dy dx for both of them. And? Which you've already done for us. Okay, great. So first, find the intersection points. Second, find dy dx for both. Okay, so yeah, the intersection points are going to be 3, 4. There's actually another point at -3, -4. Which you can do, plug in 4/3 x, you get a quadratic, solve, you get two values. Okay. So let's go ahead and do this then. For the first function, what's dy dx? 4/3. For the second function, dy dx we'll have to find implicitly. So we get 2x plus 2y times dy dx. which equals 0. Solve for dy dx. You get minus 2x divided by divided by 2y, or just minus x over y. Okay, and we do exactly that. So now we check at 3, 4. The line, our dy dx value is equal to what? The original. The line is just going to be 4/3. And yeah, you're one step ahead. Circle. Plug in the x and y coordinates into the function. So we have negative 3/4. Okay, let's also look at the other point of intersection. Dy dx is always going to be 4/3 for the line. For the circle, we do minus of negative 3, so 3 over negative 4, same thing. We get negative 3/4. Okay. So, since, how do we say this? Since the tangent lines at the intersection points are perpendicular, we say the two given functions are orthogonal at the intersection points. Okay? All right. So we're almost there. Let's try another example. Show that any curve in the family y equals c1x cubed, assuming c1 is not equal to 0, is orthogonal to each curve in the family x squared plus 3y squared equal to c2. And we're going to say c2 is greater than 0 here. All right, so we keep adding a little bit more and more. First we started with finding a differential equation. Now we talked about orthogonal. Now we're trying to show a little bit more generally that y equals c1x cubed will be orthogonal to all these curves here. Okay, how do you suppose we can do that? We could. There's an easier way. Yeah, let's go ahead and differentiate both and see what dy dx look like, right? If we know what dy dx looks like for the entire family, then that'll shed some light on how they're related to one another. So, let's start with this one. Our constant. So now we're kind of putting together our first example of what we're talking about now. C1 is equal to y over x cubed. We're going to use that later. And now we'll go ahead and differentiate the equation to get dy dx equals 3 times c1 x squared. And we'll go ahead and substitute in our value for c1. So instead of c1, we have y over x cubed. So we simplify, we get 3 times y over x. Okay, so for the first family of curves, we found that the slope at all their points was 3 times y over x. Now let's look at the second equation. So here we'll differentiate implicitly again. We get 2x plus 6y times dy dx equals 0. So if you solve for dy dx, move the 2x over, divide by 6y, bless you. You get minus 1/3 x over y. Okay. So now, since the tangent lines, so I'll call them T1, all the T1s for the purple functions has slope 3y over x, and the second family's tangent lines will have slope of minus x over 3y. T1 and T2 are perpendicular, and therefore the curves C1 and C2 are orthogonal. And this is referring to the two given families. Okay? All right. We're going to have just enough time. Are there any questions so far? Okay, so we're kind of going through applications this unit. This is just one of the more tame applications talking about orthogonal trajectories of these functions. But now we're going to put everything together. And here's what it looks like. Is that good? Okay. All right. So, here's what we were trying to build up to. Let's go ahead and define orthogonal trajectories. When all curves of one family, let's call it G of x, y, and parameter C1 equal to 0, intersect orthogonally all the curves of another family. We'll call it h of x, y, and another parameter C2 equal to 0. Then we say that the families are orthogonal trajectories of each other. And of course the question is, given one family of solutions, how do we go about finding what the other family of differential equations needs to look like if they are to be orthogonal trajectories? Okay, so here's what it looks like. We have y equals, let's say we have y equals c1 over x, and we want to find the orthogonal trajectories of this family. Okay, so here's the basic roadmap, and hopefully this will make sense. In the previous example, we had two families already given to us, and we said, well, if we know their differential equations in terms of dy dx, well, we can say whether they're perpendicular or orthogonal to each other based on that. Okay, so the idea here is if I just have one family, I could find the differential equation. Okay, and once I know what dy dx is, what do you think we can do with that? Negative reciprocal, very good. And then you can find dy dx there, go backwards, and find the other family. So, very good. This is what it's going to look like. Let's go ahead and find c1, since we'll use that in a second here. c1 is x times y. And now if I go ahead and find dy dx, that'll be minus c1 over x squared. And substituting in our constant, in terms of x and y, we have minus xy over x squared, or just minus y over x. So, dy dx equals minus y over x. This is the differential equation for the first family. And now for the second family, what does dy dx have to be? Good. Okay, so they have to be opposite reciprocal. And we can go ahead and separate. This is not too bad. We get y times dy. Whoop. Sorry about that. So we get y times dy equals x times dx. So 1/2 y squared, sorry, if I go ahead and integrate, equals 1/2 x squared plus a new parameter c2. Or we could just say y squared equals x squared plus 2c2. So then now here are the orthogonal trajectories of the first family. Okay? Now, there is a little bit more in the section with polar curves. I can tell you we're not going to deal with that too much. There might be 1 or 2 homework questions about it. There's some old formula from Calc 1 that you guys studied last year. You just look in the book for it. Instead of finding dy dx, you're going to be interested in finding r d theta dr. It's kind of the same idea. Okay, we can go over that tomorrow. All right.